All right, go ahead, Arnab. The floor is all yours.
All right, where did my presentation go? There we go. So thank you once again, Pramay, for inviting me. So today I will be talking about the quantum spin liquids and some of the research which is going on in quantum spin liquids, both in our group and in collaboration with the Oak Ridge National Lab and Los Alamos and Max Planck Institute. So in the previous talk, you heard from Pramay about magnons and magnonics. Here we will be talking about a slightly different language, which is spinons, and why that is important in quantum matter. So what I will be talking about today is spin phases of matter and quantum spin liquids. I'll be talking about the Kitaev spin liquid, the material's progress towards electronics, I have a list of collaborators whom I would like to acknowledge so that I don't forget. And the main idea that I want to promulgate here is that spin liquids show stable quasiparticles and emergent chiral phases, and it has new promises towards topological quantum computation through materials design. So what do we, by the way, this is a talk that I had given in IIS Bangalore late last year. So if you were there, you might find that it's a little bit of, but it has some of the extra slides at the end. So what are spins? By spins, I just mean here unpaired electrons have a spin half moment. So spin half moment is what we are really concerned about here. You could also have spin one, spin three half, but for this talk, I am concentrating on the spin half moments because spin half moments are the ones which are most quantum. And then you have the orbital motion of the electrons. So you have a net J, which is equal to L by S, which is what I mean by the spin. So there are several spin phases of matter. And one of the ones that we really know about is ferromagnetism, which created the ferromagnetic memory, as we all know. What happens there is that if you have many spins, and if you have one spin, what happens is that all the spins start to interact within themselves and align in one particular direction. And this is an amazing property because what it means is that there is an overall state which is stored in all the spins. And this is a very robust state. How? So because if you actually try to flip one spin out in some other direction in a ferromagnet, what happens is that the spins try to flip right back. So there is a protection which is kind of built in a ferromagnet, which has allowed us to make it into memory devices. And if I look at the energy gap, here's the energy diagram here. What we find is that the up and down sectors are actually protected by a robust energy gap. And you see that energy barrier is what is finally important for the protection of the states. And so this ferromagnet is kind of a simplest example of a protected spin state where one single spin state or one single memory state is stored in many states. And they are all protected by an energy gap. Now this is actually a pretty powerful concept because it seems that you can extend this concept in many ways into many other sectors, and has also given rise to this whole field of topological protection, as some of which I will touch. And this is also contained in the phases which are being studied in many other spin phases which are being tested. For example, you have topological phases in skyrmions, you have spin glass, you have domain walls, and the discovery of these phases and how protection is built into them is actually extremely important for us to make them into devices. If we can find robust properties in them, which are protected by robust spin gaps, that's what ultimately becomes the basis for making devices out of them. So, but that's not the only phase of matter, as we know. There are other phases of matter, such as the spin ice. We have the valence bond solid, and we have quantum spin liquids, which has where the motion of the bonds can be topological, and you have various emergent symmetry to the system, something that we will be talking about more. So what exactly is a quantum spin liquid? So a picture that you would find in the internet when you type quantum spin liquid is actually a set of spins just floating on a liquid. Well, I don't quite like that picture, because here the spins, as if it seems that these are just like some ducks floating on a pond, but that's not what we really have, because here the spins can go everywhere. What we really have is that the spins are fixed in their effective spaces. They cannot move around everywhere. And that's the definition of how we have our spin liquid. I mean, the spins that we have do not move. It's only their directions that can change. So it's more like a Buddhist prayer wheel, which can rotate, but the position of the Buddhist prayer wheels don't change. So that's what is ultimately. So it's the effective rotational degree of freedom, not the translational degree of freedom, which gives rise to this spin liquid character. So and so what we also mean is that the spins are actually non-itinerant. So that's basically the point. So to understand what is a quantum spin liquid, we can understand. I mean, we know what is a liquid in a gaseous phase. All the bonds are broken, everything is free. In the liquid, some of the bonds are there, and in a solid, everything is kind of packed in, and everything is bonded to everything else, and you have long range order. In spin liquid, you have short range order. Well, that's exactly also what we have in spin systems. At higher temperature, you have fully disordered motions. So you have a high degree of fluctuations, and you get what is called the paramagnetic state, which is essentially a spin gas state. Then you can get to a liquid or nematic phase when the spins start to interact between themselves. And then finally, when you freeze all the spins out at lower temperatures, then you get this spin solid or disordered phase, and ferromagnetic is an excellent example of that. But what happens in a quantum spin liquid is that even when you decrease the temperature completely, you still get a huge amount of quantum fluctuations, and then the motions are all entangled. And the reason why you get no ordering is because of quantum zero-point motions. And that's what you have is in a quantum spin liquid, is that even if you lower the temperature to absolute zero, and even if there are very strong interactions between the spins, they cannot really order. So what we understand from quantum spin liquids is that it happens when quantum fluctuations are very high, and they are higher than the characteristic temperature of the system. And in a quantum spin liquid, the directions are all disordered. So you get highly degenerate ground states. You get many ground states. But somehow there is an overall ordering as if happening in the quantum spin liquid. And so all the motions are ordered. And to think about that, you think about just the surface of water. In water, all the molecules of water are just moving around randomly. If you look on, they're in Brownian motion. However, when you drop a stone in the water, you form ripples. These ripples are very, very ordered. They have a very nice order to them. They kind of go out in like the spherical shapes. So, and as we see that in a liquid, what happens is that although the individual microscopic motions are all disordered, there is overall macroscopic orderliness in the system, especially their motion. So that is something, those are the emergent motions that we get in the quantum spin liquid. So what we find is that in a quantum spin liquid, somehow the directions are all disordered, but the motions are all ordered, which also means that it's the dynamics which are the most important thing. And yet you won't get any signature in the statics, but you will get signatures in the dynamics. And you will have coherent short-range correlations, and the signatures of which you should be able to get in spectroscopy. And as it turns out that in quantum spin liquids, these dynamics are often topological in nature, so you can get vortices, quasiparticles, fractionalization, all coming because of long-range entanglement. So what is basically how do you get to a spin? to get to a spin liquid, you will have to somehow ensure that even though you have very strong interaction in between all the bonds, they are not able to order. And one way to achieve that is by using a mechanism called frustration. So a frustration in a very simple picture is that when you have three spins, let's say, which are antiferromagnetically interacting between each other on a triangle, so this is, you basically have a bipartite Hamiltonian on a tripartite lattice. So that's one of the ingredients that you have. And what you have in that case is that, let's say you have antiferromagnetic interaction, then turns out that at any one point of time, only one bond is satisfied. The other bonds are generally unsatisfied. So if this spin is up, this spin is down, then this spin is completely confused which direction it would want to be in. So that's basically how the frustration looks. And as we find out that these two bonds basically form something called a spin singlet pair, but this spin is basically free. So this is a spin singlet pair, or also called a dimer covering, while this spin is free. And as you can see that if you have this on a triangle, you can actually have excitations. You have multiple degenerate ground states, first of all, because this ground state is same as that ground state is the same ground state. But what happens is that if you do an excitation, what happens is that these ground states can mutually exchange between themselves because it doesn't cost it any energy. And you can see that this dimer covering can go from one bond to the other, to the other, to the other without any cost of energy. And what we also find interestingly is that there are two different types of motion you can get. One is that you can get a right-hand chiral motion, and then you can get a left-hand chiral motion. So what you can see is that just from a triangle, which is one of the simplest frustrated motifs, you can actually get some very interesting chiral features. You can get many degenerate ground states and many excited states, all from one. And now, if you take this triangle and then you extrapolate it onto a large lattice, like a large spin lattice or a large Kagome lattice, then what you would get is that you would get a superposition of several dimer coverings. So your final ground state will be a superposition of several of these dimer coverings, and that's what you will see is your signature of the spin liquid. And these dimers actually can move from one bond to the other, to the other, to the other without any cost of energy. And this motion, so it doesn't cost any energy to go from one dimer bond to the other, but these dimers themselves have a certain energy, which means that you basically have these energy modes kind of moving around in this whole matrix of spins, and which actually becomes the breeding ground for quasiparticles and fault-tolerant behavior, because you can, and for example, braiding, in braiding, famous spin liquid code is basically the toric code, where you can basically have spins producing two types of quasiparticles, in which you can form loops, braids, all of that. And this is possible because these are extremely pliable and extremely deformable ground states. So you can basically deform one quasiparticle around the other, so on and so forth. So that's what is very possible. So there are several platforms for quantum spin liquids, and based on geometric frustration, thing that I already talked about. But you can also have exchange frustration, something I will talk about. You can have something mixed, like in 3D pyrochlore lattices, or you can basically come up with a network where, like in metal organic frameworks, or chassis Sunderland model is another example, where you can have the arrangement of spins in a way where you can basically get a network, frustrated network. So each of these spin liquid platforms actually have their own topological features, and this was quite nicely, painfully compiled in two papers, one by Lucille Savory and Leon Balance in 2017, and then by Xiaogang Wen in the Zoo of Topological Phases of Matter in this another 2017 review of modern physics article. And what we find is that the motions that we have can have various types of symmetries. Now, don't go into the details of everything I put here. The main point that I want you to get out of this slide is that you can have this gapped emergent gap Z2 symmetry, you can have a gap C6 symmetry, you can have U1 symmetry, you can have spin-on Fermi surface, and each one of them have their own effective quasiparticles. So that's basically the important point that I want you to know. So with that, and the other important point is that the signatures of these quantum spin liquids are always apparent in the dynamics, as we just mentioned. So how do we measure these dynamics? So the general way of measuring these dynamics experimentally is by looking at the spin-spin correlation. So whether you have some magnons or you have something which is more exotic or topological, what you finally measure is this quantity, which is the spin-spin correlation. And then there are several types of measurements you can do in order to understand the spin-spin correlation. Of them are important: neutron scattering, inelastic X-ray scattering, Raman spectroscopy, and MR terahertz. But all of these actually measure two spin correlation functions. I don't think that, and this is one of the deficiencies of the state of physics right now, is that some of these spin liquids have symmetries which require higher order correlations to be measured, such as 6-spin correlators or 4-spin correlators. So right now, there are no good probes for measuring multi-spin correlators or loop operators or entanglement entropy. There are none. And that's something which I think that the research community will need to come up with in the next few days. Yeah, I mean, in the future. So here we will be concentrating a lot on neutron scattering. In neutron scattering, what happens is that you have an incident neutron with an incident energy and momentum. It gets scattered from a sample, and you get an exiting energy and momentum. So the overall momentum transfer is given by the difference of the initial and final momentum. The overall energy transfer is given by the difference of the initial and final energies. Now, as it turns out, that neutrons have two properties. One is that they have a mass, and they have a de Broglie wavelength. And because of that, you can actually look at the atomic correlations. But another very important property which neutrons have, which makes it so special, is that they are chargeless. That's important because if it was charged like electrons, then it basically goes into your material and then changes the band structure. And it doesn't interact with the electrons directly, unlike X-rays, which also kind of starts to excite the system. So neutrons are pretty forgiving from that standpoint because they are chargeless, but they have a spin. So it does create a spin 1 excitation, and the propagation of the spin 1 excitation is something that you can check. So it can give you the spin-spin correlations very nicely, and the dynamic spin-spin correlations very nicely. And so what you get as the intensity is basically the dynamic scattering cross-section, which if you Fourier transform, you get the spin-spin correlation. In fact, if I write out the whole equation completely, this is the dynamic scattering cross-section, and this has this big equation here, but let me break it down for you. So if you have two spins which are at positions alpha and beta, this is the dynamic scattering cross-section which relates the two spins at alpha and beta, and then you have sum over the entire lattice. But if you break down this equation for you, the first is some constants. You have something called the magnetic form factor, which actually is extremely important because it tells you, analysis of the magnetic form factor tells you which part of the spectrum is coming from phonons, which part of the spectrum is coming from magnons. You can completely separate them out, which is nice. You have some selection rules, which helps you select which spin sector you are kind of scattering out of, because only the perpendicular components of the spin fluctuations contribute, or the spins contribute to the scattering. So that is what this term means. But the most important term is the Fourier transform of the spin-spin correlations, which is what we are trying to get to. So many of these experiments are done in the Spallation neutron source in Oak Ridge, Tennessee, and some of the experiments are done in NIST and ISIS. There is also one at Spring 8 facility in Japan where these experiments are done. I can go into much more detail about this facility, how this all works. There is a linear accelerator, there is a storage ring, and then very high energy protons hit a mercury target right here, and then there are several instruments on both sides of the target where you capture the neutrons and then you moderate them first and then you measure them. So and at the end, and one of these end stations that you see here, in fact, this one right here that I'm showing is basically this humongous giant thing here where this is the HYSPEC or the hybrid spectrometer at Oak Ridge National Lab. Whereas you see, this is how it looks. This is where the sample sits. You can fit a Dilfridge here, a dilution refrigerator here, or a very strong magnet here. And your sample goes right into this spot. There are polarizing optics here, polarizing optics there. And this whole drum that you see can move. This is the 2 theta arm. This can actually move on this floor. These are on air pads and can move on this floor. And so that's how you kind of move and do these measurements. My student here on Dixit basically is now stationed there and is doing an experiment. So then here you have graphite monochromators. The monochromatic neutron beam comes here, scatters from the sample, goes into the detectors. And this is a very large 2D detector array. So incoming neutron beam, you can have a 14 split core magnet, and this is the hovercraft, which is the detector vessel. So and this is how our samples look. This kind of goes right there. The sample is kind of right there, and we have to fix the samples very carefully so that they don't move in a magnetic field. So as you could see that the way we do this experiments is using something called tomography, where we have to constantly rotate the samples, and we do a 4D reciprocal space tomography to capture all the entire brilliance and capture the entire signals. So the detectors are 2D, but we can get 3D signals in that way. We basically stitch together all the 2D slices from every rotation, and that's how we can get it. So and one of the final things I will say about this neutron scattering is that in conventional magnets, where you get magnons and phonon, so this is basically a magnon mode. If you do the Fourier transform of that, and then you do the neutron scattering analysis, so if you look at the neutron data, that is, this is 2 reciprocal lattice directions, and red is more intensity, black is less intensity. What you get is this nice cones, and these cones are basically coming from the parabolas, which are directly related to the magnon or the phonon dispersions. So that's how the data looks. So as you see that you can basically make a cut at lower energies, you will get this nice tiny circular features. But if you go to higher and higher energies, the circular features will become larger and larger. So it's basically like a cone, which is kind of flowering. So these conical features are what you see when you have magnons, but that's not what you have when you have spin-ons or so in magnons, as you see, magnons is basically the motion of the spins between each other, like this, almost like a dance. But in a spin-on, what happens is that the spins completely flip, and then the flipped spin kind of travels everywhere in the lattice. So if you have that, that can come if you have very strong spin fluctuations. And if you have strong spin fluctuations, what you would see are basically pretty broad features in the energy momentum space. And that comes from the fact that when you have spin-ons and you have a high degree of fluctuations, the lifetime of the spin-ons are small. If you have a small lifetime in real space, in energy space, it means that the interaction, that that your energy dispersions will be pretty broad because it's the Fourier inverse. The same thing is true for correlation length. If the correlation length is long, then you get very sharp bragg peaks. You get very sharp peaks in the Fourier space. If the correlation length is short, you get very broad features in your momentum space. Same for lifetime. If your lifetime is long, you get very sharp features in energy space. If your lifetimes are short, you get very broad features. So this is something that we kind of constantly look for when we do this scattering analysis. And short lifetime and short correlation length is a telltale signature of fluctuating moment. And as we see that if we really have fractional spin-ons, for example, in this Heisenberg antiferromagnetic chain, you have a spin one, you have a spin flip, let's say. This is an antiferromagnetic chain. You put a neutron there, it produces one excitation, and that can actually break up into two solitons or two domain walls, which can now propagate in various directions. It can move all over the lattice. And when it does that, you basically produce two spin halves, which can go everywhere. And if you look at the dispersion of this system, what you find is this effective continuum of states, which are right. So you basically see the manifold coming from the antiferromagnet, but then you see this effective continuum of states. So you get this broad excitation spectrum from the spin. So this broad excitation spectrum of spin-ons, which is predicted from the beta suds, has already been measured in various materials such as KCOF3. And this is also the broad spectrum which people are lookout for when they look out for quantum spin liquids. Now let's change gears and come to something that I have been working quite a bit, which is the Kitaev quantum spin liquid. In a Kitaev quantum spin liquid, what happens is that you have three magnetic interactions in a Y type of a motive, where each magnetic interaction has a different quantization axis. So let's say that so it is a sum of three Ising terms, JXX, JYY, and JZZ, where each of these Ising terms are on different bonds. And what that means is that the spin in the middle is completely frustrated because the red bond tries to pull the spin in one direction, the blue bond tries to pull the spin in a second direction, the gray bonds try to pull the spin in a third direction, so that spin is completely frustrated. Now extrapolate it to a large lattice, like a honeycomb lattice. What you find is that it is made up of a Y, an inverted Y, a Y, an inverted Y, so on and so forth, which means that all the spins are actually frustrated. And this, as a result, leads to something called a Ising quantum spin liquid ground state, because all the bonds are Ising, and which is basically a superposition of several of these highly degenerate solutions. So you get a highly degenerate ground state, and the final ground state is basically a quantum spin liquid, which is basically superposition of all these solutions. So several of these solutions. So then the question is that what Kitaev figured out is that this is a platform that can produce non-abelian anyons. So what he was able to do is that he was able to take the spin sectors on a single honeycomb loop, and he was able to figure out that there is a conserved quantity, which is the flux operator, which means that the product of all the 6 spins on every honeycomb actually is a constant number, which is either +1 or -1. And so you have 2 fluxes, so either a +1 flux or a -1 flux. And the way to understand that is that they are like vortices. So you either get vortices or anti-vortices in the way the spins are exciting. And from that conserved quantity, what you could do is that you can actually then decompose, you can do a Jordan-Wigner transformation, and you can decompose the entire Hamiltonian. You can rewrite that entire Hamiltonian in terms of just static and dynamic Majorana fermions. So what he figured out is that there are 2 types of excitations in the system. One is this gauge fluxes, and one is this Majorana fermions. There are two types of magnetic fermions. There is this, at every bond, there are these static Mariner fermions, which are these BJs, and then you have these dynamic Mariner fermions, which are the Cs. And you basically, from all of this, you get three superselection sectors. You get the fusion of the Mariners, which basically gives you a fusion of two fermions, gives a boson. So you have bosonic sector, which is the vacuum fluctuations, and then you have the vortex sector, which is the sigma sector, and then you have the Mariner fermion sector. So fusion of two Mariner fermions gives you just a boson. That's the number, that's one that you see there. But these Mariner fermions can also interact with these fluxes, which kind of keeps the fermion parity kind of conserved throughout the system. So the way to understand this more intuitively is that if you look at the excitations in the system, there are two different kind of excitations. One is this vortex excitation, which are like these dimer coverings kind of breaking in this kind of circular pattern. And so if you have closed loop excitation, so those are the visons or the fluxes. And if you have open loops, if you basically take a scissor and cut that loop, at the ends of that loop, so then now it becomes a string, and the ends of the string basically are nothing but these itinerant Mariner fermions. And these itinerant Mariner fermions can basically they can propagate all over the lattice. And Kitaev pretty much solved this entire ground state. And what he figured out is that there you can get both gapped and gapless spin liquid states depending on the relative interactions between this JXX, JYY, and JZZ. And when JXX or JYY win out, you get these hashed phases where you basically get gapped abelian spin liquids, which complies with the toric code. But when you are in the gapless phase, what you get is these non-abelian excitations. And the way you get to those non-abelian excitations is by producing a very tiny magnetic field. What that magnetic field does at the level of perturbation is that you basically get this gapless, in a gapless spin liquid, you get this gapless Mariner fermion band structure. But what a tiny magnetic field does is that it slowly starts to gap it out. And you can produce this a band structure which is now slightly gapped by this magnetic field. And it's actually below this gap that you get these chiral edge modes. So what he was able to figure out is that when you apply this small gap, you produce four superselection sectors. One is that of the gapped bosons, which is the trivial sector, which is the magnon sector essentially. But you also get this bulked gapped emergent Mariner fermions. And you also get, along with that, this gapped Ising non-abelian anions. So you get this third very interesting sector of non-abelian anions. And finally, you get this gapless half-quantized chiral Mariner modes, which basically are the edge modes. So this is a system which has a non-zero Chern number. So it basically has this edge modes because it is a topological system, which means that if you do a fractional quantum Hall effect, you would be able to you will be able to kind of see this edge mode, the effect from this counter propagating edge modes, and you can do fractional quantum Hall effect studies on the system to see those. So those edge modes are what we are looking for, and this type of a dispersion that was predicted by Kitaev, this gapless and gap dispersion is what we are really looking for. And that is kind of the basis of the rest of much of what I will be speaking. As it turns out that people have figured out how to calculate the spectrum of neutron scattering and what the spectrum would look in. Neutron scattering, in fact, there are several papers on that, but now we needed to find a material. So one of the recipes of finding this quantum spin liquid ground states in real materials is to find how we can produce magnetic frustration in liquids. And you can produce frustration in many ways. But for making this Kitaev spin liquid ground states, you needed this very weird type of frustration where you needed each bond to kind of face a different direction. And the recipe for that was given by the seminal paper by George Jacquelin and Guignard Kaliulin in 2009, where they figured out that if you have a very strong spin orbit coupling and you have a honeycomb lattice of cations, which is surrounded by an octahedral cage of anions with a very strong spin orbit coupling on the cation, then what happens is that all the unnecessary Heisenberg interactions kind of tend to cancel out, and you are just left with 3 Ising interactions on 3 bonds which face 3 different directions. So essentially, if you look at, these are the cations, which are the spin halves, and these are the anions. And if you have an octahedral cage, you will have 3 bonds which will face 3 different directions, and the Ising interaction will be along those bonds. It will be kind of, so you can see that here the cation, anion forms these tiny squares. This is a square, that's a square, that's a square. And each of the squares face a different direction. And turns out, because of good enough Kanamori rules, the Heisenberg interactions cancel out, and your Ising interactions basically come perpendicular out of these 3 squares. So that's how you produce the Kitaev interactions. There are several material candidates which you can study and which have been proposed for realizing this state. One material on which I have worked quite a bit on is alpha ruthenium trichloride, which was basically discovered by us independently from the Toronto group. And we did some of the first measurements on the samples, some of which I will be talking about. There are many other candidates with varying degree of success. In fact, there is the new candidate, which is barium cobalt arsenate, which we have also created in our labs, which was first proposed by Peter Armitage and Bob Cava, who made the first crystals. But we also have them in our lab where we are doing measurements on them. I will not be talking about that in this talk. But as you see that most of these materials, basically none of them are really spin liquids. And the reason is that all of them form some kind of a long range order. As you see the magnetization, the ordering temperature, all of them order, none of them form spin liquids, they form an ordered state. And the reason for that is because you get these other interactions, other best terms in the Hamiltonian, such as the Heisenberg term, the off-diagonal term, which are all symmetry allowed, which means that you can really remove that. Which means that, is it true that there is really no true native quantum spin liquid in a zero magnetic field, or is there one? And even if you get some quantum spin liquid behavior, you have all these terms which are subleading in the Hamiltonian. Then the question comes is that, okay, then you get something like approximate spin liquid ground state. You see some spin liquid-like behavior and some magnon-like behavior. And then the question is that good enough? Is approximate spin liquid good enough? And what are the main themes that we should be looking for? So that became the crux of my research going ahead. And this is going into the research part of my talk, which I will go through a little bit faster because I'm running out of time. So there were some beautiful experiments done in sodium iridate where they showed these bond-dependent interactions in resonant X-ray scattering. And then there was our paper where we showed that in alpha ruthenium chloride, you get these signatures of these Marana fermions with neutron scattering. What we showed is that this material is not quite at the quantum critical point, not quite in a quantum spin liquid state, but it was pretty close, where at low temperature, you do see some zigzag type magnetic, antiferromagnetic ordering, but when you go to slightly higher temperature and you kill those zigzag ordering state, you get some of the quantum critical behavior coming in from the quantum spin liquid, excitations. So we have a large amount of experiments that we have done, including we have done scanning tunneling spectroscopy measurements. We have done several thin film measurements. We are actually trying to We have excellent data on platinum, ruthenium chloride heterostructures with Yongchen's group, where we have looked at those excitations not using neutron scattering, but using spin Hall magnet resistance for platinum. So that's a paper that is hopefully going to come out very soon in Proceedings of National Academy of Sciences. And so we have a lot of work going on here. We will be mostly talking about the neutron scattering results, though. So in neutron scattering, one of my earlier results showed that this is the intensity versus energy. So you're looking at the density of states. The density of states not only shows these sharp magnon modes, which are the bosonic modes, you also get this nice band of continuum. And as we know that bands or band structures come from fermions. So, and when we saw that nice band, what we were able to conclude that there is something more happening here, which is interesting, which is that the only way you can get a band there is if you consider that you have Majorana fermions in the system, which is forming these fermionic band structures. And so that's it. And these are magnetic Majorana fermions. So we see them in neutron scattering, and that's what we started to conjecture. And as we see that we have really two-dimensional interactions, this is another plot that we did in the science paper where we have, this is the one direction, two inclined directions. So if you look at the scattering in the plane, you get this nice star-like features, which not quite match the pure Kitaev calculations. So this is essentially quantum Monte Carlo calculations in the pure Kitaev state. We don't quite get that, but if you squint your eyes, you will see that you have a star here. You can also see a couple of stars in the flanks. And that kind of starts to match what you see here. You can see that you have almost star-like feature coming up here. But what we found is that if you take this pure Kitaev excitations and you produce a little bit of, you put a little bit of extra interactions in there at the level of a random phase approximation, that is, so you do a little bit of perturbation away from it, you can get to the star-like features, what we see in this material. So, which means that we are probably simply connected to the Kitaev phase, and we do truly have approximate spin liquid ground states where there's a high probability that this fermionic continuum that you see is probably coming from just Majorana fermions. So there were other groups who confirmed and also sharpened our claims, which was very nice to see. And there were several measurements that came up using ESR, using Raman spectroscopy, using NMR, terahertz, that we did. One important point to understand going forward for the last part of my talk is that it is extremely important in which direction you apply the field in this sample. As it turns out that this is a topological material and it has a non-zero Chern number, but those Chern number is non-zero for not all directions of the field. So it turns out that if this is your lattice, then you define this axis as the b-axis. So this is the armchair axis. And then this is the zigzag axis, which you call the a-axis. So it turns out that you have a non-zero Chern number only when you apply your field along a-axis or along c-axis, but you don't get a non-zero Chern number when you apply the field along b-axis. In fact, if you apply the field along b-axis, you would probably just get gapless excitations, which are just mostly magnon. While if you apply the field in the where you have the Chern number as non-zero, that's where you get these gapped excitations, and you will basically get these nice spin-ons. So, so our next result, what we did was that we were trying to basically apply the field along this H parallel to A, so field along this axis, cutting across these bonds. That's the direction in which we apply the field. And what we figured out is that it is indeed possible to get rid of the long-range ordering. And here's the phase diagram that we got. What we got is that at low fields, you have a zigzag antiferromagnetic order, goes into some kind of spin reoriented phase at roughly at 4 Tesla, then at 6 Tesla, it seems that you have a gapless phase. So, and then goes to a quantum spin liquid phase. So we could see that in neutron scattering, as we see that we see these gapped magnons with a spin-on continuum on the top at low energies, sorry, at low temperature and low fields. Then it becomes a gapless continuum. So the gap closes roughly at 6 Tesla, and then the gap starts to reopen at 8 Tesla. So that was the nice features that we see. And then the question that comes out, that when the gap starts to reopen, is that really the Majorana gap, which was proposed by Alexei Kitaev in his paper? Is that this gap? And is this very nice spectrum of continuum of spin-ons that we see is really this Majorana, this Majorana spin-ons? So in order to do these experiments, so there were several groups who have several viewpoints on this, and I'm not going into the details of these, but one very important result came out is that there was this group of Kasahar and Matsuda, and later the Max Planck group, who did this thermal Hall measurements. And they found that right at 8 Tesla, where we discovered that you have this quantum spin liquid excitations and you have this gapped spectrum, that's where they found that you also have a half integer quantized Hall plateau in thermal Hall measurements. And they found a robust plateau phase between roughly 8 and 8.5 Tesla right here, which was very nice because that is more of a smoking gun signature. So you basically are, you can see the edge modes here, and those are the half quantized edge modes, and that's more of a smoking gun signature of what the fact that you do have Majorana fermions there, which are half quantized. And as it turns out that one of the predictions is that you don't see the Majorana fermions for all directions of your magnetic field. You only see them along certain directions, which is nicely laid out in the Liu and Bruce Norman's PRL paper in 2017. And it turns out that that they indeed did not see any quantization when they applied the field along the B-axis, but they did see a quantization when they applied the field along the A-axis. So some of these results, these results are somewhat debated in the community because the Max Planck Institute people basically saw the same quantized Hall plateau. However, they saw it at a slightly higher field. And then it was repeated by another Japanese group, which also saw it at Matsuda saw it at 8 Tesla. They saw it between 10 and 12 Tesla. And then the Max Planck group thinks that it's now published in Nature Physics. It's actually between 10 and 14 Tesla. And then some of our own measurements with the Princeton group basically did not see the quantized Hall plateau in some of our samples, which were grown using CVT method, which is different from the Bridgman technique that they are using to grow their samples in. And so there is a lot of sample dependence here, where we saw these nice quantum oscillations, which looked very much like Shubnikov-de Haas type oscillations. There is another very nice, interesting paper which came out, which does the heat capacity studies, and they applied the field along those two directions. And this is now published in Nature Physics by Tanaka in 2022, where they showed that if you apply the field along H parallel to A, you indeed have gapped excitations, while if you apply the field for H parallel to B, you have gapless excitation. So that was that's very nice. And then they could map out how that phase diagram of gapped versus gapless excitations would look like for various directions of the magnetic field. Because now that also matched with Kitaev's predictions. Now, but what we were trying to see is whether you get those same results in neutron scattering. Now, in neutron scattering, we do have one disadvantage, that we cannot probe all parts of the brilliant zone. We don't have 3D detector arrays which go everywhere. We could only measure along one scattering plane. But we were only looking in one horizontal scattering plane. And when we applied the field, and these are very new results. So can we actually turn off recording?